was to give some convenient description of coordinates on Teichmuller space of modular spaces of Riemann surfaces of G with n boundary components, which Sasha talked a few minutes ago. So I will skip almost all biographical remarks, and just mention that it's based on papers of Volodya Hock and me, and in parallel by papers on Rinat Kashayev, and all was started from the description by Penner and Hock of a function group for Riemann surfaces, which we obtain in the Poincaré uniformization. That means that any Riemann surfaces is obtained by the quotient of the hyperbolic upper half plane under the action of the Fuchsian group, which is a subgroup of the projective group Bcl2R. There is a lot of coordinatization in this case, and the question is what are so-called physical quantities we want to obtain. And physical quantities we are going to obtain are first, they are observables. And in this uniformization picture, the observables, which must be, of course, invariant under the choice of parameterization, are lengths of geodesics on the Riemann surface. And these lengths must be mapping class group invariant objects. And what we have and what we want to obtain is to obtain some graph description of this Teichmuller space, all the same convenient graph description of the elements and conjugated classes. What we have so-called representing graphs, and these graphs are fed or train track or ribbon graphs, which are drawn on Holt or punctured Riemann surfaces. And that's why first we need at least one puncture, one boundary component, because faces of the graph correspond to holes or boundary components. And if we have some graph, then we have at least one face. And for instance, and for example, you may consider the torus with one hole. It looks like this. And on this torus, I draw the three-valent graph, which make a partition of it of this time. So we have exactly one boundary component. So we have one hole inside, and we must identify the opposite sides of this in order to obtain usual torus. On this torus, for instance, we see that there is one selected geodesics which go around this bottleneck, and no one other geodesic may intersect it. Next is that if we have a three-valent graph. Okay. Not now?
Not now.
If we have a three-valent graph, then we can easily calculate the number of edges of this graph, and this is 6j minus 6 plus 3n. And we know that the real dimension of modular space, or the same Teichmuller space, is 6j minus 6 plus 2n. So we have n extra elements if we associate somehow some variables with edges, and in order to get rid of them, we must find out some algebra that have exactly n central components corresponding to n Okay. And let me just say a few words about how to actually relate graphs and surfaces. And for this, let me consider again the same simplest example. So we have even more simple, because here we have a torus with one function, not just one boundary component, but just a function. So this corresponds not to whole, but to just to the customer. Okay. So, and then we may consider the fundamental domain corresponding to the actual function group, and split this fundamental domain into two so-called ideal triangles. It's the first one and the second one, or the zeroth one and the first one. And what we obtain as edges of the graph are Möbius type transformations that maps some selected triangles with vertices infinity, -1, and 0 to another triangle, ideal triangle with vertices at -1, 0, and the point e to the power z, where z is now a real number, and z is just z will be just the number that parameterize the corresponding Teichmuller space. And then one can easily trace out that if we want to construct the element of the function group that maps this zeroth triangle into the ideal triangle, which has mark 2, and this is exactly what we need, because then this arc goes to that arc. Then we can make it in 4 steps. First we map this triangle into that one, the selected one, with these vertices. Then we rotate this. Then we again apply this Möbius transformation and map this obtained triangle into some other triangle. Then after another rotation, we obtain it. And on the language of graphs, that means that we just make the pass inside the graph. So when passing one edge, we obtain a Möbius transformation. When rotating at one point, we are at this vertex, and we must choose one way, left or right. So we come to another edge. Then Möbius transformation again correspond to passing through this edge, and the last rotation correspond to coming to the initial edge. So if we abbreviate this action as xz1 with the Möbius transformation corresponding to this variable, L corresponds to rotation at one vertex, xz2 corresponds to this, passing through this edge, and R corresponding to the final rotation to this edge, then we obtain just some product of 2 by 2 matrices of this form, and this product would correspond to the element of the function. It turned out that this is a general consideration. So if we have just arbitrarily complicated graph corresponding to the surface of Pyrogenus and the surface with the number of boundary components, nevertheless, this consideration works well, and we may consider, okay, this set of one-to-one correspondences. So we have now real numbers Zi associated to each edge of the graph, and there are 4 one-to-one correspondents, well, 3 actually, because one of them follows from 3 others. correspondences between conjugacy classes of Fuchsian group, then the set of closed geodesics on the Riemann surface itself, then the set of closed paths on graph gamma which represents this Riemann surface, and eventually conjugacy classes of the first homotopy group of this Riemann surface. Why I set here this any of the graph? Because, of course, this procedure is not uniquely determined. For instance, if we come back and consider this splitting of the fundamental domain into ideal triangle, there is another choice of root. And this choice corresponds to so-called flip transformation on this graph. And in general, flip transformation looks like this. So if we have splitting on two ideal triangles, we can, of some ideal quadrangle, we may do it in two ways. And these two ways correspond to changing the graph. And we know that, as I said before, that the physical observables would not depend on such choice, on such flip transformation. But these flip transformations are just the transformations that we need to obtain actually a mapping plus group transformation. Okay, but coming a little bit back, we see that now we have an explicit parameterization of the path in the graph using these three matrices. And if we consider the proper product of this over this path, then we may find out the length of the physical geodesic. If we just take a trace of this element, then what we obtain a double hyperbolic cosine of the length of physical geodesics on the Riemann surface that correspond to this element. And in what follows, I will miss terms because when we will talk about intersection of geodesics, it means that we consider intersection of two actual geodesics. When we say about the products of two geodesics, that will be the products of two geodesic functions of this type. So, and the first we have is a famous skein relation, and it's purely classical and follows just from the identity which holds for any 2 by 2 matrices A and B with the unit determinants. And it has this form, but on the language of crossing geodesics, that says that if we have two crossing and look at it in the microscope, then irrelevantly of what's going on in the rest of the graph, we have this relation. That means that here -1 stands to the power which is the total number of geodesics in the whole graph. And that means that each such crossing in classical case can be disentangled. So if we have a product of geodesics, of intersecting geodesics, we may always say that this product can be presented as a linear combination of what we call geodesic laminations. And geodesic laminations is by definition a set of non-intersecting and non-self-intersecting geodesics.
What is the set in which this equation is used?
This one. L here is in this case is just a product of geodesic function, but not an arbitrary product, but the product of the functions which correspond to non-intersecting geodesics. That means that we can draw this, not the length, but the geodetic function. So it's a little bit more involved because it's hyperbolic cosines. Yeah, just a product.
Wait, well, what is the upper equation? I don't understand what it means.
This one.
Yeah, I don't understand what being equated means. We have a number or being equated?
Equated is a product, again, a product of these geodetic functions.
The number, total number of geodesic is a total graph. I have no idea what you mean by that.
That means that we have a big graph, so somehow these ends are connected in some way. But they may be connected in arbitrary way. Say if we connect 1 and 4, and corresponding to 2 and 3, then we have one geodetic here. But if we connect 2 and 4, then we have 2 geodetics. And if we, for instance, if we have 2 geodetics here, we have one geodetic here and one here. Then that means that this product, then, if I put it in the right-hand side, then this product is the sum of these 2 geodetic functions. Next step is already not so obvious, and this is to introduce the Poisson structure. The Poisson structure on the space of these z parameters. But it's introduced in a very simple way. So if we have 3 edges coming in one vertex, and we have zeta parameters corresponding to these 3 edges, then the Poisson bracket between these parameters in the cyclically ordered way is just unit. It's a simple observation that then the geodesics around poles are central elements of the Poisson algebra. So we have this sum of zeta parameters coming around boundary confidence, then it Poisson commutes with everything.
What Poisson algebra are we talking about?
Poisson algebra of these zetas.
What?
Of these zeta parameters that we associate with edges of the graph. And this means that we have exactly n central elements, and this is what we need, because then we have Poisson leaves corresponding to having the real dimension of the modular space or Teichmuller space.
Why is this the right Poisson?
Hmm?
Why is that the right Poisson?
That's a good question. We don't know why. But let me postpone it to the last part of my talk, because there are arguments from very different sort of theory, but these arguments support strongly this assumption. And this comes from a theory of 2 + 1 dimensional gravity.
Is it possible for particular parameter that happens? Was it both there and
In this case, it's just a definition.
sort of local property that's on a general
Yes. No, but then the Poisson structure of function of z, of zetas, of course, is obtained from this Poisson bracket by obvious properties. So that's I just don't write it, but that's obvious how to obtain the Poisson bracket between functions depending on zetas. Next step is what is going on to be the classical mapping class group transformation. And this comes like that. So in terms of zeta parameters, A, B, C, D is stand for zetas corresponding to these neighbor edges. It looks like this, and actually it can be obtained just from purely geometrical reasons, because you have this hyperbolic geometry, and then we can uniquely obtain this function phi, and this is logarithm of 1 plus e to the power z. And then there are two lemmas. First lemma is all geodesics functions are mapping class group or modular invariant with respect to this transformation. The second lemma is that, and it's a little bit weaker because second lemma claims that the above Poisson brackets generate the first, of course, this transformation respect this Poisson brackets. But second is that if we consider now the Poisson brackets between two intersecting geodesics, then it has exactly this form. So the objects that comes here are the same as in skein relation, but you see that we have minus sign instead of plus sign, and that's it is because the Poisson brackets must be antisymmetric with respect to interchanging these two.
John, let's say your question to the
You must be a neighbor.
With respect to the symplectic structure of the Teichmuller space, with respect to the imaginary parts of
well, this is one way, but the other way, which is quoted from our consideration, comes from 2 plus 1 dimensional gravity.
It's not actually the same as all these.
Yes. Well, I'm afraid I must skip a part devoting to modular groupoid, unfortunately, but let me just say just 2 words. So we may now this modular groupoid corresponding to morphism between 2 graphs, and groupoid means that we have morphism not between arbitrary 2 graphs, but only between 2 graphs related by Philip transformation. But if we have these morphisms, that the first property is obvious. So the inverse morphism or repeated morphism is just an identity transformation. Then if we have such a morphisms on 2 disjunct edges, then they are commute. But that's again quite obvious. The non-obvious property is so-called is the pentagon identity. That's a set of 5 consecutive morphisms on 2 neighbor edges, and it has this form. So if we start, say, from this graph, this subgraph, then the set of 5 transformations makes this graph the same. And if we just calculate the corresponding transformations of the functions on zeta variables, then we obtain the identity. That is called the pentagon identity. But in classical case, it follows obviously from just a geometrical consideration. Now let me proceed to the quantization of this algorithm. The quantization is, in this case, is just astonishingly simple. Because we have a Poisson brackets that were just numbers, then we claim that the corresponding commutator between the quantum objects must be expressed as a constant 2 pi IH times this Poisson bracket. And that obviously means that because these commutators are just constants, that we may always come to PQ basis of this algebra. Next is what will be a quantum flip transformation, or more correctly, quantum flip morphism between two algebras corresponding to two different graphs. It has the same structure, the same form, except that instead of the classical function phi, we must introduce a quantum function corresponding to this morphism, and this function appears in papers by Fadeev, 95, in a little bit different context, and it called somehow a quantum dialogue. It was called a quantum dialogue function. And of course, the most non-trivial verifying that this is a quantum function corresponding to quantum flip transformation is to check the pentagon identity for this quantum transformation, which was actually done. And next is what is a quantum geodesic length operators in this picture. And again, on the physical language, we must introduce now the ordering, because here, before we had just a trace of product of matrices, but now the items that comes to this product, they are not commute. And this means that we must consider, instead of just usual product, we must be accurate with it. And what we actually have is that this is a sum of some exponential. It's always the case, and exponential of sums of these zetas, and we must add just some constants in some cases, and we must somehow control the adding of these constants by the following rules. The first is that the mapping class group action must preserve the set of these quantum geodesic length operators. And second is a geodesic algebra. That means that the product of two quantum geodesics must be a linear combination of quantum geodesic laminations. And as we see in a moment, this product will be governed by the skein relation by Turaev. And quantum geodesic laminations is a set of, again, is a product of quantum geodesic functions corresponding to non-self-intersecting geodesics. Third property is if two geodesics are not intersecting at all, then two quantum geodesic functions commute. And this means in turn that all these functions entering one quantum geodesic lamination must commute, and this means that the order of their ordering is irrelevant. Well, there are also some other less non-trivial properties, but the most non-trivial are these three. And from the very beginning, it's not even obvious that these two properties are consistent with each other, but that's true. Huh? Well, I'll say yes. So we have quantum skein relation, and the last is that okay. So if we consider just a product of two geodesics with one intersection, then it's quite tedious, but you can elaborate this. That if we have this product, then this product is governed by this relation. So again, we must connect these ends in the proper way, and this is just a quantum derived relation. But for instance, if we consider some kind of loops or self-intersection, then it doesn't count by the quantum derived relation. It has another. There are other formulas, and this, for instance, means that if we have multiple intersections and we want to implement this quantum relation just in one intersection point, then we fail. It's not consistent procedure. And the consistent procedure is that if we have multiple intersections, then the only way is that in each intersection simultaneously we must implement this relation. And then we obtain what we need. We obtain that the product of two quantum geodetic functions is a linear combination of quantum relations. Okay, that's okay. And for instance, these relations are consistent with the Riedmeister moves. Okay, so I skip examples. And let me just, let me now just say a few words about how to obtain this Poisson algebra from some physical consideration. And physical considerations is 2 plus 1 gravity in Nelson and Ridge approach. Well, if we consider this gravity and consider the Einstein solutions of it, which has constant curvature solutions, then it turns out that this gravity can be presented as a sum of two Chern-Simons theories, which have SL2R cross SL2R gauge symmetry. And if we consider, say, one of these components, one of these theories, the usual Chern-Simons action of this type, then we know that it's topological theory with no field degrees of freedom, but nevertheless we may consider the dynamics of this theory, which comes from the kinetic term. And from kinetic term we may, by standard procedure, obtain the Poisson brackets of these guys, and these Poisson brackets have this form, and observables in this theory are holonomies around non-contractible cycles. And these holonomies in the theory are the exponents of these integrals over gamma cycles. And if we consider the Poisson brackets that follows for these quantities from these brackets, then they are exactly the same as we obtained from postulating the Poisson brackets between zeta variables. That means that, well, at least our choice is consistent with this standard theory. But some advantage of it is that actually we had Poisson brackets of very simple kind. And for instance, well, let me nevertheless come to this example because it's quite instructive. So if we have, say, 3 geodetic functions for this torus with one puncture, then we may obtain the Poisson brackets between them using skein relation and the Poisson brackets. And what we obtain for these 3 functions corresponding to 3 simple cycles will be a Poisson algebra, which is called SOQ, non-standard SOQ3 algebra, and which has this structure. So it has a quadratic part in the right-hand side. And it was not, it was obtained in Nelson and Ranger papers, and such algebras are known for, now for surfaces of arbitrary genus and for 1 and 2 punctures, and they always have these quadratic terms in the right-hand side. It was quite non-obvious how what is a good parameterization that permits us to obtain a state of quadratic Poisson bracket, just the usual Poisson brackets of the PQ type. And the only way to see it is to implement this parameterization in terms of Möbius transformation and left and right matrices. So, and just to conclude, let me say that so this is that all these things, all these theories have not only something, but have some strong arguments to do something with 2 + 1 dimensional theory. And so if we have this function group, which is a subgroup of PSL2R, we know that this is again a subgroup of PSL2C. And we know that in 2 + 1 dimensional gravity we have left and right sectors. That means that we must double the number of variables, even in topological theory. And but actually this corresponds to this picture. So what we have here? We have upper hyperbolic upper half space, and we have a slicing, and we have a real slice of this space, which is a hyperbolic upper half plane, and we have an action of function group on this PSL2R line. And what we would do in order to, and this is actually corresponding in 2 + 1 dimensional space to some trivial dynamics. So the question is, how can we get rid of this restriction to the real plane? And the way to do it is to introduce a complexification of zeta parameters in our picture. And this complexification permits us to move, at least locally, this somehow like this. So this means that at least locally we obtain a kind of Schottky uniformization for this surface, which is a surface on the absolute. If we introduce, if we double the parameters and we consider the complexification of this algebra. But this work is now in progress. So I think that.
Any 2-second questions?
I think this is what you're doing is something that for representation is a compact group that was done before, but this is the first time the foundations are done for non-compact.
Yes, seems so. But
Like your time series for non-compact.
but we need non-compact group. It's even probably more convenient to have non-compact group, because then we may consider because we consider actually non-compact Teichmuller space. We don't address the question of proper compactification at the moment. To which? Yes. There are relations. But what do you mean exactly by skein model? Because here we also have skein relations, and well, I may say that in our and Kashaev papers we can also construct a representation of this quantum skein relation, and it's it's not recent, but the last paper by Renat, he found a spectrum of quantum then twists starting from these transformations. But, well, I just had no time to touch this question. It was just the presentations of the results, which are probably 2 years old.
All right, so we reconvene in 11 hours.